In this exercise, we want to practice Taylor polynomial. So the problem is like that. Use the Taylor polynomial of order 0, 1, and 2 to approximate the value e to the power of 0.03. So the first thing is we must choose a good function and a good point. A good function for this approximation is the exponential function. And a good point should satisfy two conditions. It should be easy to compute the derivatives and the function value at this good point, and it should be close to the value where we want to approximate the function. So 0.03 is close to 0, so we choose x0 to be 0. This will be easy to compute because e to 0 is 1 and it is close to this value. So first we evaluate the function at 0 to give e to 0, which is 1. And this is enough to write the Taylor polynomial of order 0, namely t0 as a function of x. Well, as a function of x, it's actually a constant function. But still, formally, we can look at that as a polynomial, that means a function, well, this time of order 0. And this is just the value, namely 1. We can compare our approximations with the calculated value. And the calculated value for this expression is 1.030455. This is the calculated value. 1.01, well, we could call this an approximation, but we can do better using t1 and t2. To write Taylor polynomial of order 1, we need the first derivative. The derivative of this function is e to x, and we want to evaluate the derivative f prime at 0, which is again 1. So we can write t1, which will be the function value plus the derivative times x minus x0, which in this case is f at 0, which is 1, plus the derivative is 1 times x minus 0, which is x alone. So the Taylor polynomial t1 at this point 0.03 is 1 plus 0.03, which is 1.03. Well, that is good. You see, we are much closer to this value. The previous approximation was good just for 1 decimal digit. Now we have 3 valid digits. If you like some graphical interpretation, if we sketch the graph of e to x, it looks like that. And the constant was the Taylor polynomial of order 0. And the t1 linear polynomial, 1 plus x, looks like that. So here, somewhere at the point 0.03, you see that the point on the line is much closer to the exact value than the previous approximation. But we can do still better using second order approximation. For the second order, we need the second derivative. Derivative of e to x is again e to x. So the second order, and we evaluate this function at the point c, at this derivative at the point 0, which is again e to 0, which is 1. And now we can write T2, the second order Taylor polynomial, which is the function value of the derivative times x minus x0. That was the T0. These two terms make up the first order approximation, and now the quadratic term for the quadratic polynomial is in the form of 1/2 of second derivative at the point x0 times this bracket x minus x0 squared. And when we evaluate this function at our point 0.03, then we start with 1, then we continue with x. Let me write this for this function for general x. That was 1, that was 1 times x, and this is 1/2 times x squared, which is x squared half. So this is the Taylor polynomial for this second order for this function at this point in general x, and we want to evaluate T2 at 0.03, which is 1 plus x, which is 0.03, plus x squared, which is 0.0009, half of that, which is 0.000, and half of 9 is 45. So if we add all this together, we arrive at 0.03045, which is still better, still closer to the exact value, calculated value. The only difference is that nothing here, but 5 here. So these two, so we differ at this place. So this is good, 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 this is good. 1, 2, 3, 4, 5, 6 valid decimal digits. So this was the approximation, this was the application of Taylor polynomial to find an approximation of a given expression of a given number.